The sound you're about to hear was never recorded. Listen. No guitar. No microphone. No sample library. Every one of those 97,000 audio samples was computed from one equation. Today, we don't just simulate a guitar string. We make it sing. Start with the string at rest. Now, what does your finger actually do? It grabs one point and pulls. The rest of the string has no choice but to stretch into two straight lines. A pluck isn't a smooth curve. It's a triangle. Let go, and watch very carefully. This is the real solver output, slowed down. The corner doesn't melt into a gentle wobble. It splits into two corners, two kinks racing along the string, bouncing off the fixed ends, inverting, and crossing each other, over and over. If that bouncing and inverting looks familiar, it should. This is the wave equation from the last video. Same equation. Same solver. Same reflections at the fixed ends. The only thing we've changed is that now we're going to listen to it. So how does a moving string become sound in your headphones? Pick one point right here, near the bridge, where a guitar pickup sits, and just watch it. Write down its height. Then again. And again. 44,100 times every second. Here is the list of numbers, drawn as a curve, the first 50 milliseconds, straight out of the solver. Jagged, buzzy, alive. And here's the punchline, a list of 44,000 numbers per second is digital audio. There's nothing to convert. The simulation output is already a sound file. So let's do exactly that. The whole note, 2 seconds of it, written to a WAV file, and played. Watch the cursor, you are hearing this exact curve. A string doesn't ring at one frequency, it rings at a whole family of them at once. The harmonics. 110 Hz, 220, 330, and up. Here's the question, and make a prediction before I show you. We plucked dead center. Which harmonics do you think survived? Lock it in. Here's the real spectrum of the note you heard in the intro. Look at harmonics 2, 4, and 6. Gone. Not quiet, gone. Every even harmonic was silenced by where we put our finger. Here's why, and it's beautiful. Look at harmonic 2's shape. It swings on both sides of a point that never moves, a node, and that node sits exactly in the middle of the string. Your finger pulled the one point that harmonic 2 cannot move. So it never got started. And the middle is a note of every even harmonic pluck there, and you silence all of them at once. That gives us a rule you can test on a real guitar tonight: pluck at 1/5 of the string's length, and harmonic 5 vanishes. Watch bar 5. And this recipe of harmonics is what your ear calls tone. And now the exact
Listen to
same
the middle
string,
plucked
same
hollow,
note,
round,
plucked
almost
almost like
to
a
the bridge.
clarinet. Every harmonic wakes up, and the sound turns bright and twangy. Same equation. Different finger position. Completely different voice. One thing still separates our simulated string from a real steel one. A real string doesn't just resist stretching, it resists bending, like a very thin beam. In the equation, that adds one new term, a fourth derivative, fighting sharp curvature. And that term does something sneaky. High harmonics are the most sharply bent, so stiffness punishes them the most, pushing their frequencies sharp. The dashed lines are where the harmonics should be. The bars are where the stiff string actually puts them. Watch the drift grow. Can you hear it? Here's the ideal string. And this is why concert pianos are tuned wrong on purpose. Piano strings are thick and stiff, so their harmonics all run sharp. If a tuner set every octave mathematically perfect, the instrument would sound out of tune with itself. So they stretch the octaves, deliberately mistuning the piano so that it sounds right. That century-old tuner's trick is this one choral term. One last ingredient. From the derivation 2 videos ago, the wave speed is the square root of tension over density, and the pitch is C over 2L. Turn the tuning peg, tension rises, C rises, the pitch climbs. Which means our solver doesn't just make A. It can make any note we ask for. So here are 4 tensions, 4 notes. And here is your simulation, the same 2 lines of number PY from the wave video, playing them. The simulation just played you a melody. Every pitch, every timbre, every decay physics, computed 44,000 times a second. No black box, and no instrument either. Everything you heard is on the GitHub below, the audio rate solver, the stiffness term, the melody script. Change the pluck point. Add a second string. Make it play your own tune, and post it in the comments. I will listen to every one. And next time, we push on a column. Nothing happens. We push harder. Still nothing. Then, at one exact load, it snaps sideways. The eigenvalue that decides when structures buckle. See you there.